Everyone. In this video, we are going to start chapter 7, which is all about substitution and elimination reactions. Now, just a quick note, if you have the second edition of the Klein textbook, substitution reactions are covered in chapter 7, and elimination reactions are covered in chapter 8. So from now on, the chapters are all going to be one off of each other compared to the third edition of the Klein textbook. So to make things easier for everyone, I'm going to cover substitution reactions first, and then I'll cover elimination reactions in a couple of weeks. So if you have the third edition of the Klein textbook, you'll notice that they start with SN2 and E2 reactions, so substitution and elimination reactions, and then they go to SN1 and E1. So the way I'm going to go through the chapter will be a little bit different. I'm going to, again, just start with the substitution reactions and then go on to elimination. So we might be going a little bit out of order from what the chapter 7 has. All right, now this chart that I put on the slide here, this will make more sense as we go through each of the different types of reactions. So don't worry about this chart for now, but this does come from your textbook, and it's a way of summarizing what type of reaction will occur depending on what type of reactants you have. So let's start by introducing substitution reactions. So let's say that you have a reactant that has a leaving group on it. So Lg stands for leaving group. And then let's say our other reactant is a nucleophile. So Nu equals nucleophile. And then let's say they react and we end up with a product where the nucleophile has replaced the leaving group, and then our other product is just the leaving group that has gained some electrons. So now it has a negative charge. Now remember, a nucleophile is something that has a lone pair of electrons that it can donate. And sometimes that also includes having a negative charge, but not always. Now, there are two different ways that this reaction could occur. We could either have a two-step process or a one-step process. So let's say option 1. Let's say the leaving group leaves on its own in the first step. And then in the second step, the nucleophile replaces the leaving group. Now there's another option where all of this happens in one step. So the nucleophile attacks the other reactant, and the leaving group leaves as a result. So again, in option 1, there are 2 steps. In option 2, there's only 1 step. So let's look at option 1 in a little more detail. And if option 1 occurs where we have a 2-step process, we call this SN1. And that might not quite make sense just yet because there's 2 steps, so why is it SN1? But we'll talk about what SN1 means in a bit. So let's redraw our reactants. So again, in this type of reaction, the leaving group is going to leave on its own first, and the nucleophile just doesn't do anything. So what we end up with is a positively charged carbocation. So in this case, it's a secondary carbocation, but that might change based on our reactant. And then we have a nucleophile again that hasn't done anything yet. And we also have our leaving group that gained electrons. So it is now negatively charged. And then in the second step, the nucleophile is going to be attracted to anything that's partially positive or fully positively charged, right? We talked about that in chapter 6. So the nucleophile is now going to attack that positive charge, and it's going to replace the leaving group. So then we get our products that we saw on the last slide. Okay, so we have reactants on the far left. We have an intermediate. And then we have our products. So what does this look like as a reaction coordinate diagram? So we've got our reactants, and the leaving group will leave our first reactant, and then we have our intermediate, and then that reacts, and we end up with our products. Okay, so remember that the activation energy is the difference between the top of that barrier as well, and the bottom of the, sorry, my pen wasn't working, it distracted me. So the activation energy is the difference between the top of that hill and the reactants. And we'll label this first one EA1. And then we do have a second activation energy, and that will be the difference between the top of that hill and the intermediates. So that is EA2. And then remember, delta G is the difference between the reactants and the products. Okay, so we can clearly see that the first activation energy is much larger than the second activation energy. So that first step of the reaction is going to be our rate limiting step, right? Because the rate of the reaction really depends on how quickly that first step goes. All right, so the rate limiting step depends on that first activation energy. So the rate limiting step depends on the leaving group leaving. So how quickly does the leaving group leave? What that tells me is that the rate law really just depends on that first reactant, because additionally the nucleophile doesn't react in the first step. So the rate of this reaction does not depend on the nucleophile. So the rate law is equal to the rate constant times the concentration of our first reactant that has the leaving group on it. Now this is where the name SN1 comes in. So the S stands for substitution. The N stands for nucleophile. And the 1 tells us that we have a first order reaction. And if we look at our rate law down below, that is a first order rate law. The other way you can think about this is it's a unimolecular reaction. So this reaction really only depends on one reactant, or the rate only depends on one reactant. So even though this is a two-step process, this is still an SN1 reaction. I used to get SN1 and SN2 mixed up all the time because I thought, well, this is a two-step process, so it must be SN2. But that's not what the number is referring to. The number refers to the type of rate of reaction. So this is a first order reaction because the rate only depends on one reactant. So try to remember that because it's very easy to get them mixed up. In fact, maybe we should come up with a different naming scheme. All right, so now let's look at option 2. So in option 2, this is a one-step process where the nucleophile attacks and the leaving group leaves. So that's going to be our SN2 reaction. Okay, so in SN2, we have the same reactants, let's say, but this time the nucleophile is going to attack the carbon that the leaving group is bonded to, and then the leaving group leaves as a result, because otherwise we'd have a Texas carbon. So then the nucleophile replaces the leaving group, and we end up with our leaving group with a negative charge. So if we draw the reaction coordinate diagram for this reaction, again, there's really only one step here, so we're just going to see our reactants going over that barrier to the products. So we don't have any intermediates in this reaction. But again, we can determine the activation energy by taking the difference in energy at the top of that hill at the transition state and the reactant energy, so that's EA. And then delta G is the difference between the reactant and product energies. Okay, so in this process, the rate limiting step is just the one step that we have, right? And we can see that that one step involves both reactants. So the nucleophile attacked and the leaving group left. So the rate limiting step depends on the nucleophile attacking and the leaving group leaving. So if we write the rate law for this reaction, it would equal a rate constant times the concentration of the molecule with the leaving group times the concentration of the nucleophile. Now, because the rate is a second order rate law, that's where we get our name SN2 from. So the S again stands for substitution. The N stands for nucleophile. And then the 2 stands for second order reaction. Or the other way to think about this is a bimolecular reaction. So there are 2 reactants and the rate depends on both reactants. So again, just because this is a one-step process, that doesn't mean this is a SN1 reaction. The number, again, depends on whether you have a first order or a second order reaction. Okay. So how can we tell whether we have an SN1 or an SN2 reaction? Oh, that says SN2 or SN2. That should say SN1 or SN2. Here, I'll replace that and I'll fix it in the slides. So yours will hopefully say SN1 or SN2. Okay, so SN1 or SN2, how can we determine if a reaction is SN1 or SN2? So if you have an SN1 reaction, then again, the rate depends on the one reactant, right? So we're going to call that one reactant the substrate. And I'm just going to abbreviate that sub. So sub is the substrate. And again, that will be the reactant with a leaving group. And then if you have an SN2 reaction, that's going to depend on the substrate and the nucleophile. So it's a second order reaction. So again, Nu is the nucleophile. Okay, so what we can do is we can change the concentration of the nucleophile because that's the only thing that's different between these two rate laws. So let's say, okay, I'm going to change the concentration of the nucleophile. If the rate does not change, then that means we have SN1. Because again, an SN1 reaction is a first order reaction, so it does not depend on the concentration of the nucleophile. But if the rate does change, that means that our reaction rate does depend on the nucleophile, so that has to be SN2. So again, this is an easy way just to figure out, do I have an SN1 reaction or do I have an SN2 reaction? And this is more of an experimental way to determine what type of reaction you have. What we're going to do in the next video is figure out, just through theory, whether we have SN1 or SN2. All right. So I'm going to stop here, and again, in the next video, we're going to talk about, how do we know theoretically that we have an SN1 versus an SN2 reaction. All right, so I will see you then.